everybody. In this video, I'm going to go over APEX Study Section 3.2.3, and we're going to talk about polarity and intermolecular forces. So if you remember, this was actually the very last thing we were doing together before we left for COVID. So some of this is a review, so I'm going to move through it a little bit more quickly, but we did not get to intermolecular forces, and that's why we're going to back up for a second before we move forward to a new unit. I just want to make sure that we have an understanding of intermolecular forces because we're going to need it. So first is the difference between intramolecular bonds and intermolecular bonds, okay? And I know we had a difficult time with this when we were in class together. So intramolecular bonds are the bonds that hold together a molecule. So ionic and covalent bonds, which we talked a lot about, are examples of intramolecular forces. So for example, if we have a water molecule, it's our oxygen and our hydrogens. This here that holds the hydrogen to the oxygen is an example of an intramolecular bond. It's a bond that holds the individual molecule together, okay? And we've talked a lot about these. Today we're going to talk a little bit about intermolecular forces. So intermolecular forces, also called intermolecular bonds, are bonds that hold different molecules together. So you need to have two different molecules in order for this to work. Okay, so here I'm going to draw two water molecules. Okay, and these water molecules still have these intramolecular bonds. They still exist, okay? But if we have two water molecules and they are attracting to each other, then they also have intermolecular bonds, okay? So this attraction between different molecules is an intermolecular bond, okay? All right, so that's the difference between intra and intermolecular bonds. Today we're going to focus a little bit more on the intermolecular bonds because we talked a lot about intramolecular before. So when we're talking about intermolecular bonds, we need to have a good understanding of polarity. So polarity we talked about again before we left. In covalent bonds, we know that the atoms share electrons. If they share the electrons equally, when the atoms have the same electronegativity, they form a nonpolar bond. If they share the electrons unequally, which happens when the atoms have different electronegativities, they form a polar bond. So, for example, if we have, let's say, two chlorines, okay, and they're bonded together. These have the same electronegativity, so they're pulling the electrons the same amounts, and as a result, the electrons are evenly spread out. Okay, so we have equal electronegativities. They're the same atom. So electrons are equally spread out. And this makes this a nonpolar bond. Okay. Now, if we have a water molecule, okay, we know that oxygen has a greater electronegativity. We know this because it's further to the right on the periodic table. So that means that the oxygen is attracting the electrons more, so they have an unequal sharing of electrons. And that makes this a polar bond. Okay, so all of the electrons are closer to this oxygen than they are to the hydrogen. And as a result of that, we talked about how that means there's more electrons over here, so this gets a partial negative charge. And since there's less electrons on the hydrogen, they get partial positive charges. Okay? So this is an example of a polar bond. However, there's a difference between a polar bond and a polar molecule. So for a molecule to be polar, it must have unequal sharing of electrons and be asymmetric. So let's take a look at what that means. So if we have something like BF3, boron trifluoride, okay, fluorine has a greater electronegativity than boron. So this is an example of a polar bond, right? So fluorine has more electronegativity on it than that boron does, okay? However, this is a symmetric molecule. All of the electrons are missing from the middle and they're all on the outside. So they sort of cancel out. And because this is symmetric, this is not a polar molecule. So this is a non-polar molecule. So we can see that even though it has polar bonds, it's not a polar molecule because it is symmetric. However, if we have something like water, oxygen, we know, is more electronegative than hydrogen. So all the electrons are going to be in the middle, okay? And this is not symmetric. So there's more electrons up here than there are on the bottom of this molecule. So this has a polar bond, and it's asymmetric. So as a result, this is a polar molecule. Okay, so you need to check whether it's symmetric. Symmetric meaning that even though there are atoms that are more electronegative than others, they are spread out equally around the molecule, whereas this, the more electronegative atoms are on one side of the molecule. Okay. So polar molecules have what we call a dipole moment. And this causes polar molecules to attract each other, and that is an example of an intermolecular force. So going back to our water example here, okay, we know that the oxygen has that partial negative, right? Because the electrons are closer to the oxygen, and the hydrogens have a partial positive. We also know that positives and negatives attract. So this oxygen end of one water molecule is going to attract to the hydrogen end of another water molecule. And this forms an intermolecular force. Okay, so whenever we have a polar molecules, they have an intermolecular force, okay? And when we say dipole moment, that just means that there is partial negative on one side and partial positive on the other, okay? There are actually 3 different types of intermolecular forces. There's dipole-dipole, hydrogen bonding, and van der Waals forces. And if there is a stronger intermolecular force, the molecules attract more to each other. So the first type is dipole-dipole, which is what we already talked about. Okay, and this is between polar molecules. Okay, so if we have something like hydrogen chloride, then we know that the chlorine is partial negative, the hydrogen is partial positive, because that chlorine attracts the electrons more. So they attract, the chlorine attracts the hydrogen, and this is our dipole bond. Okay? Now, there's another type of dipole bonds called a hydrogen bond. Now, a hydrogen bond is a type of dipole bond, but it is very strong. It's a strong type of dipole bond. Okay? And it happens when we have hydrogen bonded to either nitrogen, oxygen, or fluorine. So in the case of water, this is an example of where we would have a hydrogen bond. Okay, so we would have hydrogen is bonded to oxygen here. So since hydrogen is so small, it gives up the electrons really easily. So that makes the separation of charge even greater. So this is even more partial positive, and this is even more partial negative. Okay. So this attraction here between the partial negative and a partial positive is a hydrogen bond. So hydrogen bonds are really important. They're the reason why water molecules are so closely packed together. They hold close to each other. It's also the reason why DNA is held together. So that just tells you how strong hydrogen bonds are, that they are able to hold together DNA. The last type of intermolecular force is a van der Waals force. This is the only type of intermolecular force for a nonpolar molecule. So this is between nonpolar molecules. So how this works is if we have something, let's say we have chlorine. Okay? And usually we have our electrons are all evenly spread out because they're both holding the electrons equally. But we also know that these electrons are moving randomly throughout. So it's possible that for a quick second, all of the electrons are on one side. And when that happens, we have an induced dipole. So it's like partially negative, but just for one quick second. Okay? And if you happen to have another set of chlorine molecules that are doing the same thing at the same time, except that all the electrons are on the other side, then these are going to attract. And this is a van der Waals force. So you can see that this would require a lot of chance that all of the electrons happen to be on one side for one atom and happen to be on the other. So this is why this is a very weak intermolecular force. Okay, so these are our three types of intermolecular forces: dipole-dipole, hydrogen bond, and van der Waals forces. Okay. So the last thing we need to know is that polar molecules are soluble in polar molecules, and nonpolar molecules are soluble in other nonpolar molecules. And we can summarize this by saying like dissolves like. So for example, oil is a nonpolar molecule. Water, we've already talked about, is a polar molecule. And you know that oil and water do not mix. That's because they have different polarities. However, you can mix water with other polar molecules. So for example, salt is polar, so it would dissolve in water, but not in oil. Okay? Spicy food contains capsaicin, and spicy food is nonpolar. So it dissolves in oil. So if you've ever tried to make chili oil, that's why you can make the oil spicy. Also, if you've ever had like spicy food, like you've eaten and your mouth is burning, and if you drink water, your mouth still keeps burning, that's because the capsaicin is not going to dissolve in the water because it's polar. But if you drink milk, milk is nonpolar, and so that will pull out that spicy food, okay? So what we need to know here is we need to know the difference between an intermolecular and an intramolecular bond. We need to know what polar molecules are and how to identify if a molecule is polar. We need to be able to identify the type of intermolecular force between dipole-dipole, hydrogen bonds, and van der Waals forces. And we need to be able to explain why oil and water do not mix using polar and nonpolar. Thank you very much.